about the area of a triangle, 1/2 the base times the height. I remember learning this in school and I never asked a question, so now I'm looking at it again, and it'd be good to understand why. Why is it true for any triangle the area is 1/2 the base times the height? Well, it's not obvious, right? But it has to do with parallelograms. The area of a parallelogram, inside a parallelogram, is the base times the height, because any parallelogram can be converted to the equivalent rectangle, right? You can just actually visually twist it and see it moving, and if you keep all the dimensions the same, meaning you don't distort the proportions, you will get a rectangle, the equivalent rectangle. There has to be an equivalent rectangle, and there's many parallelograms with the same area. You just keep moving the angles, right? So here's a triangle, and of course with any triangle, it may not be obvious, but you can duplicate the triangle and make a parallelogram. I think that's almost by definition of what a parallelogram is and what a triangle is. And of course there's big long proofs in Wikipedia, so you can look at those too. But this is just a simple visual description for someone that wants to see. Now they usually show this, the height and the base. What is the height? The height is the right angle, forms a right angle with the base. So a base is any side of the parallelogram. Can be a base. You can define your base, and we'll see that later. And then if you drop from one vertex, it's probably called, to a right angle with the base, you got a height. Well, that is the area of the equivalent rectangle. And how do you know that? Well, there's proofs and you can look at it, but you can also just look at this diagram right here. It shows that if you move this rectangle here over to here, now you have that equivalent, not rectangle, this triangle here. Over here, you have the equivalent rectangle, because a rectangle and a parallelogram are related. Every rectangle is a parallelogram, of course, because otherwise mathematics would have to make all these special cases, but not every parallelogram is a rectangle, obviously. So that is shown in this picture here. We just delete this triangle and move it over to here, and we get the equivalent base. Obviously the base that's here is the same base that's here, right? Because that's the definition of a parallelogram. But then no one ever talks about these strange cases. What if you have a parallelogram that looks like this, or even more warped? It could be almost a line. If it's a line, it's not a parallelogram. But if it's not a line, it could have an angle of 1 degree, right? And that's still a parallelogram. The thing you want to do is turn it on its side. So don't have the side that's going to end up intersecting with the base be off the base, right? You can do that, but it just makes it harder to visualize. So you just turn this, because obviously if we used it like this, then we'd have, first of all, we'd have to turn it a little bit to get a right angle, to get it parallel to the horizontal, right? You want one side to be horizontal to make it visually easier. And we've turned this somewhat horizontal, and you see that this is the height we're going to use, and we'll move this little triangle over to here, and we'll get the equivalent rectangle. And that, it's kind of interesting that 1/2 the base times the height is really not a triangle proof. It's more, it has to do with parallelograms and the relationship between parallelograms and triangles. And that's it. Peace out.